Okay. And this result was published in Physical Review recently, and of course you can find all details. Okay. Thank you, gentlemen.
Thank you, Nathan. Questions?
At the end there, you were calculating the ratio of the fluctuations to the mean. How did you do that? How do you calculate the size of the fluctuation?
How to calculate fluctuation B squared?
You have these mean equations.
We wrote equation for second moment, for second correlation of magnetic field, for correlator velocity, and for cross correlator. We average this equation in presence of mean magnetic field, of course. And after that, we take into account nonlinear terms by tau approximation. Of course, it's possible to do it in some sophisticated way, say NRG method or in something another way, but my feeling the result will be more or less the same. A crucial point that we've got some small scale dynamo before, and we've got some level of more or less isotropic turbulent magnetic field. If we've got total equipartition, this magnetic field will tend to zero, I mean B small square. But in a real situation, of course, the filling factor for small scale magnetic field is enough low, system in general enough far from equipartition, at least according to observation in solar situation. And in this case, what actually happens that we've got large scale magnetic field, it is tangling, and the result of tangling the system, small scale magnetic field, tends to equipartition with hydrodynamics.
What is the minimum system time scale that you need to unveil this large pattern in your data?
No, minimum.
Yeah.
70 turnover time of turbulent eddies.
70?
Yes. Unfortunately, I would like to stress for numerical guys, the main problem that first, it's difficult to calculate so long realization from one hand, and another hand, boundary condition, it's crucial. Periodic boundary condition, in our view, cannot produce these nice large-scale cells. Just continuous spectrum without scale separation.
You mean horizontal boundary?
Not only horizontal, vertical too.
But you're saying you need...
Yes, of course it's important. It's important in view that in order to produce zero gradient of temperature, we need in homogeneity horizontal plane. But of course, you've got large-scale cell density, we've got in homogenities in horizontal plane.
You're saying you need vertical, correct vertical boundaries. How can you apply this to the sun? Sorry.
No, it's in. Pay attention. Maybe I don't describe it. We, by some special position of grids, we can produce two cells in our system. So in central part, we've got strong flux of thermal energy without any boundary condition. I believe that we've got very wide plate. It will be just several rolls, periodic rolls. But important that we've got free or rigid boundary condition in that direction.
Oh, sure.
Not periodic. Yes.
Sharp.
Yes, very close. Yes. Thermal bond.
No. What sort of a boundary layer is it?
Less than 1 centimeter. Less than 1 centimeter. We didn't study carefully for technical reason in our plan to study it very carefully in the future. What actually happens in boundary.
You resolve that?
Yes. But pay attention, if we switched on grids, we destroyed this huge nice cell and we immediately produce normal gradient. Again, the main drop of temperature around upper and boundary volume, but nevertheless, now we've got a very pronounced drop in main body of turbulence. By the way, level of turbulence practically the same. Difference very small, with accelerating grid and without.
The instability you mentioned with the magnetic field is on regeneration field.
What kind?
The instability with the magnetic field. There was the growth of the magnetic field.
Yes.
And how does it relate to the structure?
Yes, it's a very good question. The main result of this instability, not simple growth, but redistribution of magnetic flux. We don't produce in this instability new magnetic flux. We just redistribute this flux. So if suppose we've got some initial magnetic field. In some places, magnetic field, new magnetic field will be in the same direction as the initial, and some places it's opposite. As a result, it will be some kind of sample of magnetic ropes, and increasing in one places and decreasing in another. So we should produce some magnetic rolls horizontal, say if initial field will be horizontal. But total magnetic flux will be the same. And of course, motion.
Do you see any change in the velocity spectrum, for instance?
But it's a large scale phenomenon. Of course we produce change in velocity spectrum, but first we study until now linear stage of this phenomenon. And from another hand, it is large scale phenomena, and we suppose that this is the initial study of instability that turbulent spectrum doesn't feel influence of magnetic field so strong. If not, we should take into account all these coefficients, QP, QS, etc.
Okay, we should move on. Let's thank Nathan again. Okay, so our next speaker is Ilkka Tuominen, and he's going to tell us about stellar nonlinear dipoles.
Actually, observations and modeling. Little bit astronomy. I have digged my 40-year-old archives and find some transparency. And this is one I found from there. I have not found the original reference with a quite hard effect. I couldn't find, but it's interesting. There is some increase in Rayleigh number. First there is no convection, then regular motion, then temporal chaos, soft turbulence, and hard turbulence. And the sun is still outside, far outside this picture. If somebody knows where it comes from, I will be interested. And then a few comments about the sun, which may be interest to some dynamo modelers or helioseismology people. That's the differential rotation of the sun, starting from the youngest sunspot group observations. Youngest means just formed, 1, 2, 3, 4 days old, and then going to the Mount Wilson Doppler measurement, and the young just for sunspots and sunspots groups, they are rotating most rapidly. That's interesting. Why? Another presentation is this: how the rotation velocity derived from sunspots and sunspots groups is declining when we go to the order groups and recurrent groups, etc. It goes down. So why? So is where the sunspots are formed, is the rotation there faster? And another thing which I have discussed, some Helios.
Microphone's fallen off.
With some helioseismic people, it's derived from the, again, from the sunspot motions. This is a butterfly diagram, and over the middle point of the butterfly diagram, the motion is to the poles, and another side of the center of the butterfly diagram, it's toward the equator. So it's cyclic phenomena connected to this torsional oscillation. So there's no average meridional motion from the sunspots. It varies according to the cycle. So another problem for helioseismic people. Okay, now I move to stars, active stars, rapidly rotating stars. This is one, Sigma Geminorum, and this is the photometry made somewhere, automatic telescopes in Arizona, many years. And the red point means strong, active spot or large spot or active longitude, and then it moves to 180 degrees to another longitude. And this original case weaker. And there is some shifts a few years, with a few years period. It was called flip-flop effect, found original by our Estonian colleague Jan Pelt, studying FK Coma photometry. So there is two active longitudes, 180 degrees from each other, but sometimes one is stronger and sometimes another one is stronger. That's an active star phenomenon. There's another star which we have studied years and years, II-Peg, the same phenomena. One strong active longitude and then another active strongest longitude and then another one, and that's with a more or less regular period. Flip-flop effect. These crosses which are here, I return later, little bit later. Now we have this famous Kraiman Helsinki joint spectrograph at La Palma. This is correct size. Correct, it's not like that. Some theorists explained when I showed it like that. It's on the telescope, about 1.5, 2 meter long dimension. We call it, traditional reason still, Sofin spectrograph. It's a Helsinki Observatory and Kryman Observatory build it together. It's very strong metal, not aluminium, lot of optics, lot of electronics inside the Earth. And this spectrograph was ready in 91. Now it's 2004, 2008. 17 years ago. And now we have observed long time series of spectra and made these temperature inversions. There are some examples where we now have located these active longitudes as a spot structure. There's more about this IIPEC from another projection. You see this is from quite in the beginning of this spectrograph. You see some evolution of these, and you can locate these to this photometric curve. The same phenomena is obtained from the temperature images derived from some inversion methods. There's something more about this IIPEC. You don't need to read it, just listen. Some examples. And now, I have also made some simple mean field dynamo calculations, which I don't, it's the normal mean field induction equation and hydrodynamics with the normal Reynolds equation with some lambda effect. You know what this is, lambda effect, and some numerical solutions with the most simple feedbacks, nonlinear feedbacks to alpha effect, to mean Lorentz force, and to what did I say? Alpha effect, mean Lorentz force, and lambda effect. And found this nice, it's just an example, no need to go to the details. It's some direction only. This Taylor number. Here is sun. A0 symmetry. And then you increase the Taylor number. It finally goes to this A1 non-axis. This is non-axis symmetric solution. Series expansion in the longitude direction. This is a non-axis symmetric solution with dominating M1 moment. This one. Just like in these active stars. And that's one of these A1 solutions. Dynamo model. This is south and north. And the magnetic field here is changing sign. It's different size, different sign when you are north or south, and then changes these signs when you go forward. And from this I made some once already some years ago some theoretical prediction which I called active star hail rule. You probably know what is hail rule in the sun. Again, hail rule in the sun, the famous sunspot polarity rule. Now it's broken. Now it's broken. I close it. So, I'm in active star hail rule. And here is this flip-flop effect, and the field changes the signs. So, how to prove these theoretical predictions? Now we have upgraded our spectrograph during several years to make the spectropolarimetric observations more accurate. It was possible also in the beginning, but there was some optical problems. We had to upgrade it with some new prism and whatever. So, but now the spectropolarimetric option is working perfectly. There are actually not in many places in the world, not even in the ESO, somewhere in Australia, a few in the whole world. It's working spectropolarimetry. And our modest size Nordic optical telescope, it's small enough to get easily long time series over the rotational phases of the star. Years and years. Now we have collaborators in Potsdam who have developed actually very good magnetic inversion code. This is just an example. These are preliminary results. It's no need to start some physical conclusions about it, it's just demonstration. This is a temperature map, and this is a map of the magnetic field. So when they have made ready the magnetic inversion code, tested everything, and we have now a few years very good spectropolarimetric data. So finally we can hopefully find solution. Is this my active star hail rule prediction correct, or should it be modified? There was also somewhere some motion picture about this Torsten Karol's derivation, but I think if Kepler is not here, it's enough. You can imagine that they are rotating. Close your eyes. That's all I have to say.
Thank you very much.
Thank you. Questions? Yes.
I was trying to understand what you're saying about the meridional flow. So we used to say that sunspots show a different meridional flow to the helioseismology. Is that just because they're anchored at a different depth? You said there was a problem for helioseismology. Is it just that the sunspots are at a different depth?
So, where the sunspots are formed, young sunspots, are they formed in the thermocline region or some upper region? Who knows? But as far as I discussed these helioseismic results with some specialists who are absolutely eager to propagate their own results, which are a little bit more critical. These meridional motions from the helioseismic they are still quite uncertain. That's maybe this would be some helpful direction for them.
Right, okay. Any other questions? Yes, right.
For the A1 mode to be the flip-flop explanation, doesn't one require this to be in an oscillatory mode as well?
Yeah, in principle, there must be some way to get some mixed mode solution is needed.
And that has not happened yet.
That's only there's some in Potsdam who had solved this induction equation. But with this, including this Reynolds equation and several 3 or more feedback effects. Nobody has made this 3-dimensional code, as we say.
Okay, let's thank Ilko again. So it's coffee time, we reconvene at 11. Dynamos with penetration, rotation and shear.
Thank you, David. I'd like to continue the slightly negative train of thought that was started by David yesterday. It's not quite true that you have to be really negative to work in Leeds, but it certainly happens. So I'm going to be talking about dynamos with penetration, rotation and shear. And I'm going to be focusing mainly on penetration. This is joint work with Fausto Cattaneo and Nick Brummel. So David gave some nice motivation for why you might be interested in understanding dynamos with rotation and shear. This is the solar cycle as manifested in Galileo's original sunspot drawings. And if we go a bit more up to date, we can see the large-scale active regions that you see on the solar surface. I think everybody would claim that this is a large-scale, well-ordered field that we're going to try and explain. And you can see it's well-ordered over successive cycles by having a look. This is a movie over 3 cycles, so you can really see the solar cycle here. Sunspots, okay, we'll let it go. Sunspots are found at mid-latitudes, and as the cycle progresses, they move towards the equator and die away. Then the next cycle starts, they move towards the equator and die away. And then over the 3rd cycle, the same thing. And the polarity of the sunspots has flipped, which is quite difficult to detect in that movie. But you can see that there is a large-scale field, and it is very systematic. Now, there is a small-scale dynamo, we believe at least, going on at the solar surface. At least I think everybody in this room would believe that there is a small-scale dynamo. So these are small-scale patches of black and white, black being one polarity field, white being the other polarity field, which keep appearing every time they see a black and white patch. They put a little ring around it. And this so-called magnetic carpet seems to be not really, or only slightly correlated with the solar cycle. So this is a different type of dynamo, which we believe might be working at the surface. Now, at the surface, you have very turbulent convection, as Nathan showed us earlier, and it's at very high magnetic Reynolds number. So there's no real reason to think why there wouldn't be a dynamo, except I'll show you that there have been some arguments that this is not a dynamo, to do with the penetration. This movie here is just trying to show you the form of the field that you might see in a small-scale dynamo in the corona, and how it might be important for the corona. So they're zooming in, and at some point they do an extrapolation. This is not a measurement, this is just them playing around. Okay, so we'd like to understand both the small-scale dynamo and large-scale dynamo, and one of them is a lot easier to understand than the other, I think it's fair to say. So just to fix terminology, when I say a large-scale dynamo, I mean the systematic large-scale field, a field which is generated on scales larger than the length scale of the turbulence. And these have systematic properties. For small scale, sometimes called the fluctuation dynamo, we're not really interested in any sort of systematic properties. We're talking about fields that are generated on scales of the turbulence or slightly smaller than the turbulence. Even. So we believe that large-scale solar magnetic activity is driven by dynamo action seated somewhere in the tachocline, in the solar interior, and we believe that the important place is the tachocline, where there's a strong so-called omega effect or shear that draws out colloidal field into toroidal field. Small-scale magnetic activity is observed at the solar surface, and as I said, it's not linked or linked only weakly to the solar cycle. It should be noted, and I'll point it out again, that at the surface there is a shear flow there as well, so one might be interested in the interaction of a small-scale dynamo with a shear flow. I think it's fair to say that not much is known definitively, or there's no even consensus about the origin of either a large or small-scale field. Now, okay, so the solar interior consists of a magnetised, rotating, compressible, and compressibility is an important feature in the surface layers of the Sun, but not so much towards the base of the solar convection zone. It's certainly stratified, it's sheared. This is a map of the internal differential rotation of the Sun, which we've seen before, showing that it rotates as a solid body, largely in the interior, and in the convection zone, the rotation is constant, largely on radial lines. So we have a fast rotating equator and a slow rotating pole. So there is differential rotation pretty much all the way through the convection zone. There's a shear at the surface layer. The surface layer has very vigorous convection going on, and because of stratification, there's less vigorous or slower convection going on in the convection zone. And so from the point of view of the surface layers, the rest of the convection zone appears to be evolving on rather a slow timescale. And so one might model this as a kind of penetration of a very turbulent layer into a less turbulent layer. So that's where penetration comes in the surface layers. Down towards the base of the convection zone, one has the slower convection, which is penetrating into a very stable region. So again, one might be interested in the effects of convection penetrating into a more stable region. Other things to note is that the plasma is at high magnetic Reynolds number, and all the problems, I should stress again, David was talking about this today, all the problems of getting a systematic large-scale field occur at high magnetic Reynolds number. There is no problem with getting a systematic magnetic field at low magnetic Reynolds number. So if you're doing some simulations and you're doing them at low magnetic Reynolds number and you get a mean field or a large-scale field, don't be surprised, there is no problem with getting them at low magnetic Reynolds number. All the problems come at high magnetic Reynolds number. It's at low magnetic Prandtl number, which means that the fluid Reynolds number is much bigger than the magnetic Reynolds number. So although the magnetic Reynolds number is high, the fluid Reynolds number is much larger. And this is a problem in itself as to how to get excitation of dynamo action. This is the same regime as the experiments. So you might want to ask, what are the roles of all these competing effects in driving dynamo action? If one's interested in just what's going on at the solar surface, all you want to know is, can I get a dynamo or not? Or large-scale dynamo action. Okay? And in particular, we're just going to look at these three. So you could argue, I mean, it's very easy to wave your hands and argue one way or the other, and unless you actually do a calculation or lots of calculations, then you can argue both ways in certain cases. So you can argue that stratification or penetration is good for, so I'm going to give the arguments for why it's good for dynamo action or bad for dynamo action, and good for large-scale dynamo action and bad for large-scale dynamo action. So people have argued that it's good for dynamo action because if you have penetration into a stable layer below, then this can store the magnetic energy away from the region of generation. So the back reaction of the mean field, or even of the fluctuating field, on the flow will be lessened, and so this might lead to amplification of stronger fields. On the other hand, you can argue that it's bad for dynamo action because if you lose your magnetic flux to the stable layer below, then that might mean that dynamo action switches off. In particular, Stein and Nordland have argued this, that in the surface layers of the Sun, you lose the magnetic flux that's generated by the dynamo in the surface layers, and this leads to the switching off of the dynamo. So we'll try and test this claim. You can argue that it's good for large-scale dynamo action because if you have a stable stratified, stable layer, then you decrease the turbulent diffusivity, And this may lead to get around this catastrophic quenching problem. This so-called interface dynamo scenario was proposed by Parker in 1993. It's good to have a stable layer because maybe you can store a large-scale magnetic field, and perhaps following on from Ethan's talk, you can perhaps store the large-scale magnetic helicity away from the small-scale magnetic helicity. Parker didn't quite say this, but I think he had that in mind, actually, when he was thinking about, or maybe he didn't, I don't know, interface dynamo. You could argue, again, that it's bad for large-scale dynamo action because you're losing some of the magnetic flux, and then you have to get it back somehow. I mean, maybe magnetic buoyancy provides a natural thing to do that, but... So rotation, people can argue it's good for dynamo action because it introduces coherence to the flows, decreases the randomness if you're worried about the randomness. It does introduce a preferred direction, which may help. It may lead to coherent structures aligned with the rotation. It's bad for dynamo action in the sense that for a given thermal forcing or thermal driving, it decreases the strength of the turbulence for fixed driving, but at the sorts of Rayleigh numbers we're talking about in the sun, that's not really a problem. Of course, most people argue rotation is good for large-scale dynamo action because it introduces a handedness to the flow, which might give you an alpha effect, and again introduces a preferred direction. I couldn't think of any arguments as to why rotation might be bad for large-scale dynamo action, so I think probably is a consensus in that, but maybe somebody can come up with one. Well, turbulence is clearly good for dynamo action. You have chaotic stretching of field lines leading to field amplification, but on the other hand, if one has turbulent dissipation, and this increases the dissipation. You could say it's good for large-scale dynamo action because the interaction of the turbulence with the rotation may lead to correlations and an alpha effect. These, I think, are very significant problems. You can say it's bad for large-scale dynamo action because you get this preferential generation of small-scale fields. At high magnetic Reynolds number, that's certainly true, or seems to be true. The more turbulent you are, the more random you are, leads to some lack of correlations. And as I stressed earlier, these really are problems at high magnetic Reynolds number. There is no problem at low or moderate magnetic Reynolds number. I couldn't think any reasons why shear might be bad for dynamo action. If you have coherent stretching, that's going to stretch out field lines and amplify things. It could be good for large-scale dynamo action. If you have a large-scale field there, then it will certainly get sheared out. One might imagine the case where a shear might enhance the diffusion of the small scales and leave you only with the large scales, so-called shear-enhanced diffusion. So it could remove the small-scale field via shear-enhanced diffusion. Mike talked yesterday about why it might be good for large-scale dynamo action in combination with the fluctuating alpha effect. And again, I couldn't think any reasons why shear was bad. So I guess we can say shear is good, or at least neutral. So we're just going to do some simple numerical experiments to test the importance of turbulence, penetration, rotation, and shear for both dynamo action, because you might be interested in whether penetration affects small-scale dynamo action, and large-scale dynamo action by considering two models, simple models, local Cartesian models. The first model is fully compressible and stratified, and we're really going to only be interested on penetration, effects of penetration on dynamo action. So whether losing flux into a stable layer below really does hinder the dynamo as suggested. And the second one, we're going to look in more detail at the effects of penetration and a little bit at rotation and shear. And this is going to be a much simpler model. It's going to be Boussinesq, and we're going to look at penetrative or overshooting convection there as well. So fully compressible dynamos have been studied by a large number of authors, and our formulation is again to look at a penetrative layer. So we have a convection zone on top of a stable layer. It's a local domain, so Z is depth, and we achieve a penetrative formulation by stacking two polytropes on top of each other with different adiabatic exponents, which is a standard trick to look at penetrative formulation. And we solve the fully compressible equations. We do a very simple thing. We just solve them with penetration present and penetration absent, and we say, is one better than the other? Just to test this claim. Now, I'd like to stress that this formulation is very computationally intensive, and this is not a a good way to study turbulent dynamos. In the fully compressible computations, it's a real pain. And you get numerical problems. And we have to use very, very high resolutions for cases that would just be trivial in the Boussinesq limit. But you can study the role of penetration, which is what we do. Okay, these are the equations. I don't really want to get into details, but they're fully compressible, so you have a momentum equation, conservation of mass, an energy equation, and the induction equation, and an equation of state. And we do eventually manage to get to a regime. This is the non-penetrative dynamo, where this is the vertical velocity, and this is the magnetic field. So we do get a dynamo. And as you can see, despite the fact that we've done this at massive resolution, this is not very turbulent. So we do get small-scale dynamo action. This is very small-scale dynamo action, and the magnetic energy grows. So the question is now, if we take this calculation and just put a stable layer underneath, will the dynamo switch off, as suggested? Will it get better? I don't know. Well, I do know, actually, because it's on the next slide. So all we did was we then took that solution and added in a stable layer. And there's some issue about the role of the bottom boundary conditions of the domain. So in order to get around that issue, we just took the bottom boundary as far away as we could, so it didn't actually affect the solution at all. And as you see, what happens is the magnetic field that we had before here starts to fill into the stable region by the overshooting convection. And this is a sign that the convection is acting as a convective instability. It's taking field from here, and because of the asymmetry, it amplifies it and stores it down here. So the role of the stable layer is not that it's not important that you lose field down there, because one always has a little bit of seed field down here. The plumes act so as to take this field, wrap it up, and store it down here. So on the contrary to actually having a penetrative layer, say it makes the dynamo worse, local dynamo action just seems to carry on just fine in the presence of magnetic pumping. And so here's the magnetic energy, and this is how it would have gone on if there was no penetration, and you see we get a slight increase in the energy. So I would say there's no reason why the magnetic field at the solar surface cannot be generated by dynamo action, and I think most dynamo theorists would agree.
Penetration is a large-scale effect caused by the diamagnetic or paramagnetic velocity, or it is...
No, we impose penetration by essentially, let me just go back, by essentially making the adiabatic index different in the penetrative layer to the convective. So one is convectively stable, one is convectively unstable. So we go in by hand and say, so our Boussinesq model is a lot more simple, but again, well, it's almost identical to the one David showed you earlier. It's a local Cartesian domain, but again, we can make a penetrative formulation. But this time, the way to do it is just to make one of your non-dimensional parameters, in this case, the Rayleigh number, a function of depth. So we just impose that the Rayleigh number is a function of depth, and so our Rayleigh number is positive in the Z between 0 and 1, and it's negative, so stable to convection in this layer. So that's how we make this thing penetrative. And in this formulation, it is very possible to reach very turbulent regime. And you can investigate the role of penetration, and in particular penetration in connection with rotation. Okay, I won't say too much about shear. We can impose a shear, and in this case, in contrast to David, we impose a shear which is going in the y direction, which is a function of z. Okay. And you can impose this, as David said yesterday, either by forcing or just going in there and imposing the flow, and we just go in there and impose the flow. So we have no trouble. So you can always argue, what is the force that would lead to this velocity? And the answer is, we don't know, but we would say there is a force that would lead to that velocity. Okay. So these are the equations. So these are the equations of Boussinesq, MHD, which we've seen a few times before, and the four non-dimensional parameters are here. Okay. So what is the the effect of increase of having a penetrative layer. So these are 3 different kinetic energy distributions for 3 different rotation rates with a penetrative formalism. So we impose the layer at the change from stable to unstable, z is equal to 1, and you can see, let's just pick one of these. Let's take the non-rotating case here. One has a penetration into the stable layer, so flows overshoot, the convection overshoots into the stable layer, and one has a significant kinetic energy density down to maybe z is equal to 1.5 in this case. And as you start to rotate the domain, this is a fixed Rayleigh number, of course the vigour of the convection decreases, but actually the penetration depth does not change all that much. You can change the stability of the lower layer by changing essentially the profile of the Rayleigh number, and we've done that as well. And again, the penetration depth is remarkably insensitive to these changes, and so it seems to be controlled by the convection. So it's largely independent of Rayleigh number and tail number. It's slightly sensitive to the stability of the lower layer, the penetration depth. So quite how far you get in doesn't seem to depend too much on Rayleigh number or Taylor number. So this is just hydrodynamic. And if you have a look at changing the rotation, and again this will perhaps not surprise anybody, what we're showing here is the vertical velocity halfway down the convective domain there, and this is at the base of the so-called nominal convecting layer for 3 different rotation rates. So this has gone off the edge of the thing, for 3 different Taylor numbers. And as one rotates, of course, everything goes to smaller and smaller scales. You can see here that the rotation has not really significantly affected the depth to which the convection penetrates, but it has affected the horizontal scale. And of course, now, because we're rotating, we can have some helicity, as David showed you yesterday. And this helicity, which you can see here, is now, we've broken the up-down symmetry that David had before, which we said that the helicity between 0 and 0.5 has to be the opposite of the one between 0.5 and 1. So of course for no rotation we shouldn't get very much relative helicity, and indeed we don't. As one starts to rotate, you can see that this asymmetric helicity distribution emerges. And so this calculation has a net helicity over the whole domain. So it's not that it cancels out to 0. This really does have a net helicity, and one might expect, according to mean field theory, that it should be a jolly good large-scale dynamo. So this interaction between the rotation and the penetration leads to this generation of net helicity. So it should be this one should be a good candidate for large-scale dynamo action. One would think, especially in the region just below the convection zone, because there the magnetic Reynolds number is smaller, perhaps.
In the case of absence of penetration, you have uniform rotation and homogeneous turbulence.
So that's the case
So
David
of
showed
course, in
yesterday.
this situation, mean alpha effect and mean helicity should be 0.
Okay, the net helicity over the whole domain in that case is 0.
Yeah.
But if you average over half of the domain, you have a net helicity over half the domain, and you might expect an alpha effect over half the domain, as David said yesterday. In this case, there's a net helicity over the whole domain, so you might expect a mean field over the whole domain.
Is it mean helicity or?
This is relative helicity, which is.
I mean mean helicity in the sense after how many turnover time you average this?
Okay, so we run the thing until it reaches a statistically steady state, and then we average this over, I would say about four turnover times, 4 or 5 turnover times. So, but this is a fair.
I'm sure it's not statistical noise.
No, I'm sure. I'm sure this is not. We have averaged this, over. We can carry an averaging. We have a large run, but I'm fairly certain. Maybe these details we could do a bit more averaging. But there's definitely a net helicity. You would expect a net helicity. You don't have any symmetry, and you have rotation. So, if one's non-rotating but penetrating, then again you get a nice dynamo. So this is the kinetic energy in 5 times the magnetic energy. We've set the magnetic Prandtl number to be large, which is of course the wrong case for the sun. It's very hard to study the small magnetic Prandtl number, but I believe that actually you can help yourself over studying the small magnetic Prandtl number problem in isotropic turbulence, because these convective problems, you need a lot of resolution in 2 directions, but not in the 3rd. Whereas if you do isotropic turbulence, you need a lot of resolution in all directions. So maybe you can save yourself some anguish a little bit. This is a good dynamo. This is non-rotating. And the field is very, very small scale. Almost all the energy is in the small scale field. This is not unexpected. There's no reason to expect this to generate a large scale field. Okay. But there is some sign of more of a tendency to generate a large scale component in the stable region. Although I would say there's not much more of a sign of that. So when you do, these are just pictures at different depths of the field, and these are spectra. So you might say that this does appear to be slightly larger scale field than this. This is in the stable region, this is in the unstable region, and indeed the spectrum shows that it's slightly shifted to smaller k. So penetration maybe gives you a slightly better, larger scale field, but not much. If one increases, changes the rotation, then again this is the magnetic energy and this is the energy in the mean. One thing to note is that the energy in the mean field is much, much smaller than the energy in the fluctuations. So you get more energy by increasing the Taylor number, which is kind of well understood. You can pack more field in, but you don't really get any more large scale field, even in the stably stratified region. So these should be good dynamos. We have a net helicity, good large-scale dynamos. Rotation and penetration give a net helicity which should generate a large-scale field, but doesn't. So this is really, well, I don't know if you should panic, Gandar, or you don't look panicked. So
I'm not used to such things.
Oh, okay. You just resigned. You resigned, shrug. So again, it's a small-scale dynamo. Even in the penetrative layer, the case of penetration and rotation only has a small-scale field. What can I say? It's high magnetic Reynolds number. If one adds shear, we added shear towards the base of the convection zone to give ourselves the best chance. That was where the largest scale field was residing. The problem is if you add shear, of course you increase the energy. You just shear out the small-scale field. And so these are, again, the y, in this case it's the y component of the field because the shear was in the y direction. And again, you can see that this is really dominated by small-scale field. So
Steve,
yeah.
introduce shear.
We just add an extra term to the equation. We just go in by hand and say, imagine now that there's an extra shear flow u in the y direction, which is a function of z. And I should say how big the shear is, because I know you're going to ask it. The shear is, the amplitude of the shear is about the same amplitude as the strongest flows in the convective flows. So that's the amplitude of the shear. There's hardly any large-scale components. It's a very good dynamo. It's a very good dynamo. But the shear can really, and this is the problem, the shear can really only amplify the unsystematic large-scale component. You might imagine that if you had some sort of large-scale component, then what would happen is that the shear would amplify that, and you would get a large-scale strong component. But if the large-scale component is weak, and in particular if it keeps varying in direction, then the shear has nothing really to get hold of to amplify that shear. To amplify that field, to produce a systematic large-scale component. I mean, simply put, if the alpha bit of your alpha omega dynamo is not giving you any mean, then the omega effect can do whatever it likes, and it's not going to work. And you can have a look at what the large-scale component is doing. These are not really very clear plots, but what's happening is the the large-scale field is not systematic. It's not systematically pointing in any direction. It's rotating around with time. And so even though the shear's in one direction, it has a mean which is doing this. It's rotating around. And so it's very, very hard for it to get a large-scale systematic component. Right. Okay, so shear doesn't help. So just to summarise, penetration, it doesn't enhance or diminish dynamo action in the compressible models. It enhances it slightly. So there is no reason that a local dynamo at the solar surface should switch off. I believe that it's not reprocessing of flux that you're seeing at the solar surface. It really is just local dynamo action. The Booster-Ness models with turbulence, penetration, rotation, and shear, they're great dynamos, but they're not very good at producing large-scale field. So you can ask the question, well, why is this? And in particular, this might cheer up Anvar, I don't know. If you do the similar problem in a spherical shell, which has been done by these guys, you see that they do get a nice systematic large-scale field in the stable region. And you might say, well, why are they getting a nice large-scale field and we're not? So you can compare and contrast. So the good points of each calculation are put in green, and the bad points are in red. So theirs is a moderately turbulent flow. So they're not at very high magnetic resonance number. So I would say that's very significant. And we're highly turbulent. They're global, which I think is probably useful for them, and we're local. So we have no preferred direction for the mean field. It's just as likely to go in any of the horizontal directions. And I think that's probably not so good for large-scale dynamo action, whereas they definitely distinguish between longitude and latitude, for example, because of their geometry. Another difference is that they're anelastic, which may help because they can capture magnetic buoyancy instabilities, and in particular they can capture the feedback of this large-scale field that they've generated back into the convection. If you can somehow bias the convection, then you might systematically get around this problem, and ours is Booster-esque, so there's no buoyancy. So David and I and a postdoc were looking at doing some local models of anelastic dynamos similar to the ones we've got with stratification to see if any of these results come through. We're all rotating, sheared and penetrative, and we're all in the wrong parameter regime for the sun, but maybe who cares about that? We're at high PM. Unless you believe that the small-scale dynamo and the large-scale dynamo are differently affected by the Prandtl number. They get a large-scale field and we don't, but maybe everything works with instabilities anyway, and we don't have to worry about the turbulent dynamo. So I'll stop there. Thank you.
Okay, thank you, Steve.
Okay, maybe in order to study large-scale dynamo, in a pure situation, it's better to exclude small-scale dynamo, and in this case, it's possible to.
But in a high magnetic resonance number fluid, how do you exclude the small-scale dynamo?
Yeah.
Except maybe if you go to the low magnetic Prandtl number limit.
Yes.
But but you kill yourself to do that.
Yeah.
And then you want to look at large-scale. I mean,
Yeah. In the case of shear, you have periodic shear periodic boundary conditions. Yeah.
What do you mean shear periodic?
You mean the remotion of walls, no?
Sorry?
The remotion of walls, of boundaries, no?
Motion of walls.
Like a shearing box.
Shearing
No,
box.
it's not like a shearing box.
It's not shearing
No,
box.
it's just stress-free.
Oh, okay.
At the top.
Is the degree of scale separation or the size of the box really big enough? Can you check that?
Well, when you rotate the box, of course, you get lots and lots of cells per box.
Right, but you really want to check this quantitatively.
So how big would you like it? I mean, there is a scale separation between the size of the box and the size of a mean field.
I mean, there must be at least an alpha effect in some limit.
I mean, if you have one here, there are a lot of cells.
Yes.
I mean, there's quite a lot to average.
So then you need to know what is the alpha effect that you get in any of the limits where you do get an alpha effect,
Okay,
and then
we didn't measure an alpha effect.
and then you also need to measure, of course, how big is the beta effect, turbulent diffusivity.
Well,
These are
And once you
That's a very hard. I mean, David measured the alpha effect in his problem, and it was almost impossible to measure. And I would say the beta effect is an order of magnitude.
But that was also non-linear, of course. But
These
David.
are non-linear.
Yeah, but I mean, you want to be sure that you understand at least some cases. So let's start with the kinematic case first of all,
Right.
and then there must be some regime where an alpha effect does exist, and be it at small,
low magnetic Reynolds number.
yeah, be it at small magnetic Reynolds numbers.
Yeah.
They probably are bigger than unity anyway, but.
Yeah, low magnetic Reynolds number. There's no problem.
And then you can check how big a box do you need in such a case.
But you might need a different size box for high magnetic Reynolds.
Oh, but then you go gradually upwards.
Well, that's what I mean. David looks at the effects of changing
Yes.
the size.
So what I'm after is not jumping into the deep pool and say, oh, there's no fish here, but check where you at least see something to fish for, and then see how
Right.
does
I mean,
everything
I think-
change
I
as
think
you make things
we all
harder.
find nice alpha effects at low magnetic Reynolds number. So it was like, you know, you see quite a lot of fish, and then where everybody's got the problem, you know, you've cooked your fish, you've eaten your fish, you've got chips with it, you've gone out, there's no fish. Right.
A sea of questions, probably. Andrew.
Yeah, I was wondering about two things. One is the small scale dynamo. Again, I'm still after this, where the peak is. And
Right.
where the peak is and where the resistive scale is. I mean, is that...
Okay, so these are high magnetic complement.
Yes.
So well, high 5.
Yeah,
They're
that's
not
fine.
low.
That's okay.
Yeah, and so I mean the peak is well, so you want to know the peak, where this peak of the magnetic field is
Yes.
as a function of
And then, then where is the resistive scale? Is it at...
the resistive scale somewhere down here. I mean I haven't even gone. Yeah, it's somewhere over here.
I think it's the same. I mean, if you look at such a thing, normally you need an order of magnitude for the dissipation scale. So the dissipation scale is possibly...
I mean, this peak is really, I would say, the size of the convective eddies.
Yeah, but
Maybe
that is
slightly
the
shifted, maybe slightly shifted.
Yeah,
to the right.
but there's no power spectrum, you see. So therefore, that must be at the
I mean,
same
there's
time.
no inertial range. Is that what
That's
you mean?
right, yeah.
Yeah. Well, no, I agree. But I find it very hard to. I mean, lots of people would just put a line there.
If
but
you have a high PM, there may not be an inertial range.
no, that's right. They may not.
So that may be okay, but still one would like to know where the resistive scale is.
Oh, you know, over here.
Yeah.
Just over here.
So that's interesting for the fluctuation dynamo because there's all this thing which the other side, right?
I have to say, if you're really interested in the fluctuation dynamo, then you should just look at the simpler flows. There's no point in simulating all these flows. What you need to just look at fast dynamo theory and show where, and there you can really get nice peaks in your magnetic fields for a flow on one scale. If you're interested in the high magnetic quantum limit, then
Not high, but you will find.
okay, but yeah, then look at that one because you're wasting your time simulating all these flows. You just take a nice flow like the ABC flow or Galloway-Proctor flow or something, and then you look at that because that's a lot easier to do to get to high magnetic Reynolds numbers. So I would say don't bother simulating a connection.
And what's the thing about instabilities? Last slide.
Oh, okay. So there is a separate theory which says that it's not turbulent convection at all. It's the interaction of instabilities with rotation. So imagine you somehow manage to get the large scale field at the basic convection zone. It's unstable to magnetic buoyancy, interacts with rotation, the field twists. And then you have to explain how does that work, despite the fact you have all this turbulence there mangling up the field, if you want to explain it.
Engine.
Can you go back to the slides that you had 1 minute ago before this question?
The slice, which one, sorry, Adrian?
I mean, you had a slide showing that you have the generation of net velocity for strong.
Yeah,